Good afternoon, this is Schweitzer. We're going to do a quick little video on the periodic table and just, some general information about what the periodic table looks like and things we can do with the periodic table. Um, so the columns that go up and down are quite often referred to as either families or columns or groups. And quite often we will see these guys labeled right here. 1, 2, 3, 4, 5, 8, 9, 10, 12, 15. Sometimes this is just 3A, but that's kind of how we look at their families. One thing about families is that they all have, well, we like to think of them as having similar properties. There's a lot of examples of these as you go along. Okay, a couple things you might notice here. This section right here to about here, we call this this whole area, I should say, separating here. This whole to the left is metals. To the right is non-metals. The section with X's marked here, aluminum, keep in mind, is not one of them. It's a metal. And if you go on, you'll find these are call near metals. There's a lot of little designations of, it is what it is. Metalloids. Okay, and this little section here is called the transition elements. Transition metals or elements, whatever you want. Okay, again, biggest thing from here, we have our transition metals. Now, I called this transition metals, but one thing I didn't mention, which this thing might indicate instead, is that these guys here, in fact, let's add that in there instead. Going back and forth, this thing here, any of these guys, from crossed here and there, crossed here and there, we call these things rows. Okay. Another name for a row is a period. Okay. This little section right here to right here is commonly referred to as a metal, but it's called the transition metals. Might see that more later. Okay, so next slide, guys, here. All right, metals. There are lots of properties of metals, so if you were to remember one or two, what would they might be? First of all, metals, they are conductors of electricity. We use them a lot for things like wire in conduction of, electrical wiring. Okay, so that's really good for that. Metals oxidize to form cations. What does that mean? Okay, so the number one property, if I had to pick one property of metal, it'd probably be that it's a conductor of electricity. There are other ones though. Let's add a few other properties of metals in here. You can add them in yourself as well. They're very malleable. But are all metals malleable? Not necessarily. They are very ductile. Now, is everyone ductile? No. What does that mean? It means is you need to be drawn into a wire. I mean, typically by this time we would have already done a lab called the copper brimstone lab. Copper brimstone. Now, brimstone is another name for sulfur. Okay, now can you imagine taking sulfur, since you've worked with it, and drawing it into a layer? This just isn't going to happen. Other things that metals might be, we do typically think of them as their strength, but that might be more typically um, associated with iron than other metals. But, okay. All right, so conduct electricity is another one. If I had to pick one of them, one or two of them. All right, metals can oxidize to form cations. What does this mean? Okay. Well, in this case, we know that from our last chapter that metals have a small number of valence electrons. Let's say, for example, aluminum. And in order to get a full outer shell, they need to lose those electrons. So, example would be that aluminum, okay, which typically has 13 protons and 13 electrons, will go to aluminum plus 3 electrons. It's going to lose electrons to form its standard nature in nature charge, most stable point. And now it still has 13 protons, but it's only got 10 electrons, and there's the other 3 right there that lost. So in nature, this process is called oxidation, and we form metal ions. Okay. All right, so it says complete the Bohr diagram of Bohr and Lewis dot diagram of aluminum. Okay, so just kind of talked about that. So it's got 13 positives here, and it's got 1, 2. All right, that's the 1s2 electrons, if that is where you're at. 2s2, and then 2, so there's the 2s2 here, put that there, 2s2, and we got 2, so now we need 2p, we need a grand total of 10 electrons, so 2, 4, 5, and now, if we're doing aluminum, we need to have this thing be full, and look like that. Now this is only 1, 2, 3, 4, 5, 6, 7, and 10, so technically aluminum has 3 energy levels. So we have to draw another energy level on this guy. All right, just perfectly fine. And put 1, 2, maybe a third one here. So if we take it off, that would be aluminum ion, but it just says for the aluminum atom. And there we go. Okay. When the aluminum loses 3 electrons, it's called a called a cation. And after aluminum has 13 protons and 10 electrons, giving a charge of plus 3. Another everyday name for this process is called oxidation. Okay, write out the oxidation reaction for aluminum. Did that already up top. Aluminum goes to aluminum plus 3 electrons. Now the name oxidation is very old, and therefore it doesn't really mean anything to do with electrons. So we sometimes have to memorize a little bit about the name oxidation, the definition, because the name doesn't mean it anymore. Anytime you have electrons on the product side, it's called oxidation. So that's something to remember. All right, let's keep going here. So properties of metals. Okay. Again, there we go. Malleable, ductile, luster, strong. Strong, are all metals strong? Not so much. We commonly call that twisted steel. Allows it to bend continuously without breaking. You have metals that are hammered into things nicely, pound them into shapes. So this is where we get our malleable, ductile, luster, strong. Okay. So when we say strong, we might be thinking more like iron, which really changed the human society over the course of thousands of years. You got one tribal person who's got a sword and they're trying to defend themselves. And if one person can make a sword that's a little bit harder than another person's sword, then sometime, well, history has shown us that they hack up the neighbor if they have to. So this metals and being able to forge and make metals, really important in society as we've evolved. All right, so metal reactivity. Just, is it interesting to know? Is it nice to know? I mean, Some metals are extremely, unreactive. Some are very reactive. It really varies as you go around. So there are 7 metals of antiquity. This is kind of, again, just maybe interesting to know. So what are they? Well, we have copper. Okay, we have gold, um, silver, lead, mercury, and tin, and iron. So, I mean, they're not always just seen on the Earth, but this is 7 metals that if you lived, 1,000 years ago, would be around because they're pretty much on the surface of the Earth. Not a lot, but at times, then people figured out how to take essentially rust, which is iron oxide, and smelt it back to iron. So, anyways, metals tend to get more reactive as you go to the outside edges. So these metals are extremely reactive, not so much in the middle. General trend. Okay. But again, you'll find metals that that are normally on Earth, in the rusted form, like in the oxidized form. So humans take their iron oxide, say it looks like this, FeO, and we take out the oxygen and make it into metal, and then the rest of time that it's on Earth, the air that it's submerged in is just trying to drive it back to iron oxide. Give it time, it goes there all by itself. And humans add in energy and drive it back. Whereas a metal like gold, for example, Au, this process of oxidizing gold very slow, if at all. Okay. So some metals extremely reactive, some metals not so much. Some metals very strong. Okay. And some not so much. Very reactive, not so reactive. So they all have some varying properties. Interesting stuff. Okay, non-metal properties. Okay, so the non-metal properties are sometimes just the opposite of metals, right? So we have things like non-metals have lots of properties, but what do we know about these things? Well, they're non-conductors. They tend to um, gain electrons to form anions. So we'll see more of that in a second here, but I could just pick an example here. We'll see in a moment. Let's say, for example, fluorine has 1, 2, 3, 4, 5, 6, 7 valence electrons. You'll grab one more electron to form fluoride, F -1. 1, 2, 3, 4, 5, 6, 7, 8. Okay, we call this reduction, by the way. Seems kind of strange that you'll call something that gains electron reduction, but that's because it's not really referring to electrons, it's referring to oxygen, but it's different now. So we changed the rules. Opposite of metals, pretty much property-wise. All right, so in this case, nice to know things about non-metals. So we got here. They're brittle, form lots of colors. Can be solids, can be liquids, can be gases. So melting points are wide-ranging. Okay. Again, these are things that if you looked up metals, you might say, oh, interesting. Okay. There are some reasons behind that, but it's just not the most important stuff, but kind of interesting. Okay. So it says here, write the Bohr and Lewis diagram for sulfur. So you'll find sulfur in the periodic table. It's right under oxygen. So right off the bat here, let's just kind of find it on the periodic table, and you'll find it right here. So it's not in the first row, not in the second row, but it's right below oxygen. So it has the same number of valence electrons as oxygen, but it has one more row. So it's got 3 rows. So we got 1, 2. We're going to have to add another row on this guy if we want to do elemental sulfur. Okay. Okay, and then it's got 2 electrons in the first energy level. It's got 8 in the second, and it's got 6 in the third. Okay, that's how many valence electrons it has. So 1, 2, 3, 4, 5, and 6. Okay, so write draw the Bohr diagram of Lewis dot electron dot with this guy. So sulfur 1, 2, 3, 4, 5, 6. So notice here we're only showing the valence electrons on this guy. Sulfur, of course, would like to put one more electron right here and one more electron here, and it forms a very common charge of S minus 2. Very stable point. All right, so let's see what we got here for a minute. It says, interesting, nice to know properties of these guys. They're brittle, form lots of colors, can be solids, liquids, or gases. And again, the melting points are wide ranging. Okay, so sulfur has, well, let's see here. Sulfur has blank total electrons. Okay, so it's got, let's count up here. 1, 2, there's 10, 11, 12, 13, 14, 15, 16 electrons. Also has 16 protons if it's neutral. Total electrons, but only 6 valence electrons. If given the opportunity, sulfur will gain 2 electrons, giving it a -2 charge. This process is called reduction. You're going to write a reaction out for this. It would be sulfur plus 2 electrons yields sulfide. That's the reduction reaction. I could highlight this reaction by just saying, okay, well, sulfur's got 16 protons. It's got 16 electrons. And here's 2 more. So now it has 16 protons. And how many electrons? It has 18 electrons. Okay. All right. Interesting properties. Again, nice to know stuff here about a few things about nonmetals. Antoine Lavoisier. Okay, so this guy is a pretty famous French chemist. You can go over to, let's say, Wikipedia. Let's grab this guy on Wikipedia for a second. What do you notice about this guy here? It says, let's see here. Well, he recognized and named oxygen and hydrogen, and he's got some unique views. The metric system. He's often thought of as being the father of chemistry. There we go. He's largely stemming from his qualitative to quantitative changing of chemistry. And it's neat over here. It says, executed by the guillotine. All right, nice. So, with that being said, let's kick back here. Another guy here, Fritz Haber, okay, devised a method of producing ammonia from nitrogen in air. He used it to produce ammonium nitrate explosives during World War I. Devised a process to use chlorine in World War I, in which eventually killed over 90,000 people, injuring 1.23 million. His wife was the first PhD in Germany, and she committed suicide. As a Jew, he was forced out of Germany during World War II. So there's a lot of interesting history about some of these guys and non-metals of oxygen and of nitrogen in the air. So interesting stuff here. All right, so periodic table elements. These families have names. So the name of this first family is called the alkali metals. Spelled that wrong. Alkali metals. All right, this is the alkaline earth metals. Okay, this middle section here we call the transition metals. Okay, transition metals. All the families have names. Some are more common than others. We have things here like this family here is called the halogens. Very common stuff in everyday life. Halogens. Noble gases. Sometimes these are referred to as inert gases. Sometimes on the periodic table, you notice a few other things here. Let's say, for example, Tc, deuterium. And there are a few other ones. In fact, everything beyond uranium is considered to be made by people, so synthetic. I don't know why, but deuterium is not located on Earth, apparently. Lots of varying in the transition elements. We've got metals for solid versus, liquid mercury, gold is very soft. So it is what it is. Okay. Other things that we have here. Some of them are also radioactive. Okay. Everything beyond lead, which is hiding behind the gold here, Pb, right about here, I believe. Everything beyond lead at some point is radioactive. So, let's say, for example, uranium. You are uranium. And this there's uranium. And then Pu, which is plutonium, which is both of these guys are very critical in the area of nuclear weapons. So, all right. Do you know the valence electrons? Most common in nature and most common charge. So, 1 valence electron, 2 valence electrons, 3 valence electrons, 4, 5, 6, 7, 8. This is our tipping point right here that everything to the right is going to start gaining electrons, and this guy could gain 4 electrons and then gain 3, gain 2, gain 1, and doesn't need to gain anything. Everything to the left, so this guy could also lose 4 electrons, is losing electrons, plus 3, losing 3, losing 2 electrons for a positive charge, and losing 1 electron. Okay, what's a diatomic element? Well, it turns out in nature there are 7 elements that always form together, not by themselves. And those would be N2, O2, F2, Cl2, Br2, and I2. Call it the super 7 because it forms the shape of a 7. It starts at number 7, and there are 7 of them, except that's only 6 because the 7th one is right here, H2. All right. Just some various things about the periodic table. Thank you very much.